The next speaker is Ashoke Sen of Divergence. So he will talk about semi-inclusive cross-section in three-dimensional zero-base string theory.
Thank you. So first of all, a big congratulations to Hiroshi for being such a leader in our field and being such a great influence on the generations of physicists. So I probably know Hiroshi almost more than any of you, maybe. So my first meeting with Hiroshi was in 1987 in Kanpur, okay, which I still remember very vividly. We both went for a conference in IIT Kanpur, and there Hiroshi was certainly the star of the show. Okay. So I have no memory of what I talked about in that conference, but I still vividly remember his excellent lectures on KP hierarchy in that conference, because he gave a series of 4 lectures, I think, and it was impressive on 2 counts. Okay, first of all was the amazing clarity that those lectures had. Okay, and the second was the amazing punctuality. You would stop exactly after 60 minutes. So this I have not seen anywhere else, earlier or later. It was really amazing how his lectures were. And since then, of course, we have met many times. Okay, and including my 2-month stay at Caltech, which was really memorable. Okay. And physics-wise, of course, he has been highly influential. Okay. So congratulations again. Now, going back to the days of Kanpur, I remember one more thing from those days. Okay. Before that conference, he had also written a series of papers on string field theory, which many of you may not be aware of. And we tried to tell him to start another series of lectures on string field theory, which he politely refused. And knowing him, now I can say for sure that if he had chosen to give those lectures on string field theory, it would have been as clear as his lectures on KP hierarchy. But he was probably worried about the fact that he will take 65 minutes instead of 60 minutes. So that was the reason he didn't going to give those lectures. Thank you. So today I'm going to take my revenge and talk on string field theory. So let me begin by introducing type 0B string theory in 2 dimensions, why it's interesting. So this is, you can think of this as a regular critical string theory with a somewhat strange word field theory. So it contains a free scalar, which are denoted by x naught, and its superpartner, which are Majorana fermions. It also contains a super Liouville theory with central charge 27/2. So the total central charge adds up to 30, because this one has 3. The first system, the second one has 27/2, and it has the usual superconformal ghost system. So these are the diffeomorphism ghosts B and C, okay? And beta and gamma are the superconformals. Now the main difference between type 0B and type 2B theory is the way the GSO projection acts. Okay, in type 0B theory, GSO projection acts simultaneously on the left and right side. And consequently, it has only the NS, NS and RR sectors. Okay, so only bosonic states, no NSR or RNS sectors, which would have given the formulaic states in type. So I can work on the physical spectrum of this theory, and it was worked out long time ago. And that seems to consist of a massless scalar, which are denoted by phi NS in the coming from the NS, NS sector, and a massless scalar phi r in the Ramon Ramon sector. So 2 massless scalars, that's the whole content of the theory. Now this theory, okay, has d instantons and anti-d instantons, okay, which are like normal Divergence, except that they have Dirichlet boundary condition along the time direction, as well as on all the space directions. And typically, these are obtained by imposing what are known as ZZ boundary conditions on the Liouville field, and the usual Dirichlet boundary condition on the x naught and psi naught. And physically, they correspond to finite action solutions in string theory, and they give non-perturbative contribution to string amplitudes. And those amplitudes are suppressed by exponentials of pi minus pi over gs, where pi over gs is basically the action of the instants. Gs here is the appropriately normalized closed string coupling. And we will be working in the alpha prime equal to 2 convention, okay, which there's nothing special about this. The only reason we have chosen to work with this convention is because we will be comparing our results with this paper, with the papers of these papers, these people, Balthazar, Rodriguez, and Nin, who use the alpha prime equal to 2 convention. Now, the reason that these theories are of interest is because they have a dual description, which is exactly solvable. And that's the matrix model description. So the dual matrix model description consists of free non-interacting formulas, which are denoted by psi, with single particle Hamiltonian given by this symbol. So this is inverted harmonic oscillator. The potential is unbounded from below. Nevertheless, the reason that the theory is sensible is because we have put formulas in this theory. So you can fill up the formula level up to a certain value. And then, of course, the energies are bounded from here. Okay, so the energy above the formula, the excitations are all positive energy states above the formula. So the formula level will take to be at a depth mu below the top. And when one works out the current precise relationship between the parameters of the matrix model and the parameters of string theory, we find that mu is 1/TS. Now, the formulas in this theory correspond to D0 branes in the dual string. These are unstable D0 branes. But more interestingly, the closed string states map to fermion hole pairs. Okay, so the fermion hole pairs are the low energy excitations of this system. Those can be shown to be mapped to closed string states. In particular, if we introduce the density operator psi dagger psi, they create fermion hole pair excitations. And it's the states created by rho which correspond to mass, which can be shown to correspond to some massless scalars, chi L and chi R on the left and right side of the barrier. Okay, the fact that these are massless scalars, of course, had to be proved. Okay, it's trivial. And once we have this a pair of massless scalars, then we can relate it to the massless scalars that we saw on the string theory side. Okay. And after normalization, the relationship between the two is that the NS sector scalar is the sum of the scalars from the left and the right, and the Ramon sector scalar is the difference between the scalars on the right and the left. Now, we can compare the perturbative string theory amplitudes with the amplitudes that we calculate in the matrix model. So the perturbative string theory amplitudes get mapped to matrix model amplitudes, where you throw in a fermion hole PR from one side, okay, and it gets reflected. You could do it from the left side or the right side. Okay, those can be translated to appropriate linear combinations of the NS sector and Ramon sector states. The effect of the tunneling is that when you throw in a fermion hole PR, okay, a hole can tunnel or the fermion can tunnel to the other side. That effect is captured by the D inside. So those are non-perturbative from the point of view of the matrix model as well as from the point of view of string theory. In particular, we use the convention that D incenters correspond to the effect of fermion tunneling from right to left, or hole tunneling from left to right, which are essentially the same thing. And anti-D incenters do the opposite. They capture the effect of the hole tunneling from right to left, or fermion tunneling from left to right. So based on this picture, you can see that a D incenter, what it will do is that if a fermion hole pair comes from the right, it transmits the fermion to the left, and it reflects the hole back to the right. So an incident fermion hole pair from the right, it will go into a fermion on the left and a hole on the right. But this has no regular closed string description. Okay? Closed string states are fermion hole pair excitations. So D incenters, the final state of a scattering induced by D incenter doesn't seem to have a regular closed string expression, a closed string description. And this theory has its counterpart in the string theory computation. So in string theory, as we'll see in detail later, the de-incidental amplitude in string theory, what happens is that this effect shows up as infrared divergences in the annulus parts. And these infrared divergences essentially makes the amplitude vanish when there are finite number of external closed string states. Okay, so we'll see how this happens. And the goal of this talk will be to try to define appropriate infrared finite semi-inclusive cross-section induced by de-incidental. And this will be similar to what we do in quantum electrodynamics in 4 dimensions. And then once we define appropriate semi-inclusive cross-section, we'll try to compare the results on the string theory side with the matrix. So that is basically the content of this. And here comes the main references for this. Okay, in the semi-inclusive cross-section will be based on this paper. So with this, let me begin by describing how we go about computing de-incidental. Now, what particular feature of de-incidental amplitudes is that individual worldsheets do not conserve energy and moment because of the Dirichlet boundary connection in the time direction. Energy is not conserved, so individual worldsheets do not conserve energy. Okay. Similarly, they do not conserve the Liouville moment. As well as we can have disconnected worldsheet because we don't have normally in disconnected diagrams. The reason that we don't include disconnected diagrams even in quantum field theory is because they impose special kind of momentum conservation. Okay, other than the overall momentum. Okay? Because each connected component has its own momentum. But this doesn't happen for de-incidental induced amplitudes, and as a result, we can have disconnect. So let's now see what is a leading de-incidental contribution that we get. So this now, as in in string theory, the contribution to a given amplitude is proportional to GS to the power of Euler number. Okay. And this has Euler number -1. Okay. So we can gain parts of the coupling, inverse parts of coupling by simply maximizing the number of disks. So the leading contribution comes from maximizing the number of disks. So you can have, here I have denoted how to maximize the number of disks. Basically, each external closed string you insert it on one disk. Okay, so you use as many disks as the number of closed strings. You can also have empty disks, but that's part of the exponential of the de-incidental action, which is of course which accompanies all de-incidental action. Furthermore, the annulus has no suppression in powers of GS. Because the annulus is Euler number 0, so it goes as GS to the 0. So you can have as many annulus as you want without introducing any power of G string. So you have to resum the annulus contribution. So you have an exponential of the annulus. So this is the structure of the leading de-incidental induced contribution. There is the exponential suppression factor, the exponential of the annulus, and then the product of the least one. Let's focus on the exponential of the annulus. Here, this expression one can work out. Okay, just by doing the worldsheet computation of the annulus partition function. And this is what one gets. Okay, for this case, the result is simple. It's just minus integral 0 to infinity dt over 2. So t here is a modular parameter of the annulus. In particular, you can say this is the ratio of the circumference to the width of the annulus. Now, as you can see, the exponent, this integral diverges both at large and at small. Now, it turns out the divergence at large t is associated with open string 0 modes. And these, in fact, can be made finite. So we'll see how to do this. These can be treated using open string field theory. And this will discuss in a few minutes. On the other hand, divergence at small t can be shown to be associated with infrared divergence in the closed string channel. And this is the reason why we say that the de-incidental induced amplitudes vanish. Okay, because every amplitude has this exponential of the annulus. Okay. And even though we can make sense of the divergence at large t by open string field theory, the divergence at small t is genuine. Okay, and the amplitude indeed is 0. And this, as I said, reflects the impossibility of a single D-center process to produce finite number of final state closed rings. So let's now turn to the next base case, which is a D-incidental anti-D-incidental induced process. From the matrix model picture, you can see that the D-incidental anti-D-incidental induced processes shouldn't have the problem of the kind that we discussed, because they are to have a fermion hole pair coming in, both fermion and hole can get transferred. So it will appear on the other side as a fermion hole pair. So the result shouldn't vanish. So it can produce a regular closed ring in the final state. And we will see this. So what is the difference? What the difference, first of all, is that the overall factor is the exponential of minus 2 pi over Ts, because there is D-incidental action and the anti-D-incidental action. The exponential of the annulus amplitude will be replaced by exponential of the sum over annulus. Okay, so this is the annulus with both boundaries on the D-center. This is the annulus with both boundaries on the anti-D-center. And this is an annulus with one boundary on the D-center and the other one is on the anti-D-center. And finally, that each this one-point function is now replaced by the sum of the one-point function with the D-center boundary condition and the one-point function with the anti-D-center. And here I have written down the expression for this expression, although we will not really need this in detail. So here, let me just explain the various formulas. So x1 and x2 are the positions of the D-center and the anti-D-center in the time coordinate, time direction. Sigma is the x value plus or minus 1. So this is plus 1 if the closed string is incoming, and minus 1 if the closed string is outgoing. Omega E is the Euclidean energy, which is minus I times omega. Omega is the energy of the closed string. And Pu is the Liouville momentum that the closed string carries. So there is a very explicit expression for what this part object is. Okay. So as you can see, everything in this formula is actually explicitly known. So you can evaluate it, except that there are divergences that you have to deal with. So this is an expression for the exponential of the annulus, which was divergent already. And here is an effect. So this is the result we get. So minus 2 comes because minus 1 from this diagram, minus 1 from this diagram. And this contribution is coming from the annulus with one boundary on the incident and the other boundary on the annulus. You can see, first of all, that the small t divergence has gone away. Right? There's no divergence in this integral from the small t region. And this is what we expect, because now the closed string integral divergences shouldn't be there, because you can actually get a regular closed string state in this scattering process. The divergence from large T region is still there. Okay, this is the open string channel divergence. So the divergence because of this minus 2, right? This represents the effect of the open string 0 volts. And then this term can diverge when x1 minus x2 is less than 2pi. When x1 minus x2 is less than 2pi, as you can see, because this becomes a positive coefficient. And that divergence can be associated with the fact that there is an open string tachyon coming from the state of the open string that is staged between the incident and the anti-incident. When the peak goes, there can be tachyon. So let me describe the strategy that one uses for dealing with the large divergence. Yeah, but this is not going to be the main topic of this talk, so I'll be brief on this. Here is the set of steps that one follows in dealing with this large divergence. So how to make sense of the divergence that comes from the large series. First, we use a series of identities. All these identities are valid when HB and HF are positive. First of all, this integral one can show is given by square root of HF over HB. Okay, this is an mathematical identity. Second, HB to the minus half we can write as an integral, a Gaussian integral of this form. HF one can write as a Gaussian integral of this form, where these are Grassmann objects. Now, using this, so recall that the expression that we had in the previous slide was of this kind, right? Except that here HF and HB was 0, right? When this -2 coefficient was the exponent was that's e to the 2 pi minus 2 pi HBT, HB was 0. But otherwise, the structure of the expression is similar. So what we do is that we interpret the modes phi b, pf, and qf as open string fields. Zero dimensional open string fields, because they are really living on the instant one, right? So the open string field is a big word, right? These are really open string modes, you can say. And the exponent, these factors to the minus half HB phi b square to the minus HF, PF, QF, these can be shown to be equal to what we get from the open string field theory action written in the single gauge. Okay, so these exponents basically is the open string field theory action. Now, the idea is that when HB and HF are 0 or negative, we forget about the original expression and we try to use these expressions to make sense of the divergent results. Okay, that what happens when what is the meaning of HB equal to 0? Right? This was divergent, this is also divergent because the phi b integral of course diverges. Okay? But in this form, we can try to make sense of these divergences better. Okay? And that's what we'll try to do. First of all, modes with HB less than, right? This will diverge because you will have the integral d phi b with exponents of the positive phi b's, for number times phi b's. But once you think of these as integrals over the modes, we can try to make sense of these by carrying out the integration along the steepest descent. Okay? Because after all, instant terms are the saddle point for the path integral. And in order to evaluate the contribution from a saddle point, you always follow the steepest descent formula. So we try to make sense of the modes with HB less than 0 by using the integration, by carrying out the integration on the steepest descent contour, which basically means that you can continue to use the same formula with an extra minus. Right? HB will now be negative, so there's an extra R. And that is simply a reflection of the fact that the phi b integral is now running over along the imaginary axis instead of the real axis, because the steepest descent contour runs along the imaginary axis. The simple issues are with the modes with HB equal to 0 and HF equal to 0. These represent respectively the bosonic and the harmonic 0 modes that T1 needs. Okay, and these are the modes that have to be treated carefully. Okay. So in the next slide, I'll summarize how these modes are treated. So in the present example, it turns out that -2 actually is a result of having 2 bosonic 0 modes and 4 harmonic 0 modes. Okay, this you can find out by examining the open string spectrum. Okay, if you look at the spectrum in the single gauge, okay, you find that there are 2 bosonic states and 4 harmonic states. So what are these 2 bosonic 0 modes? So they in fact have a very simple interpretation. They are associated with the freedom of translating the instanton and the anti-instanton along the Euclidean time range. Right? Because of course, once you have an instanton, you can place it anywhere. Okay, and that degree of freedom is showing up as bosonic 0 modes on the instanton. So the remedy here to deal with these 2 bosonic 0 modes is to change variables from the bosonic 0 modes to the instanton positions x1 and x2. And in that process, we'll pick up some Jacobian forms. Now, besides this bosonic 0 modes, you also have 4 harmonic 0 modes. And that's the reason for getting that -2. These start up to come from the ghost anti-ghost pair on the instanton and the anti-instanton. And this requires some explanation. So where is the ghost as anti-ghost pair coming from? Okay. So for this, let's recall that if you have a DP plane, the regular DP plane, we know that it has a U1 gauge field living. And you have to gauge fix when you quantize. So when you quantize the U1 gauge field, you get a pair of other ghost fields. Now, when you have a D instanton, okay, this U1 gauge field actually is not there. Okay, and the U1 gauge invariance becomes a rigid gauge, rigid transformation, because it doesn't depend on, there is no space-time coordinate to depend on. So it is a symmetry that is not supposed to be gauge fixed. Unfortunately, string field theory tries to put all the DP blades on the same footing, and as a result, the way string field theory is or way the one-sheet theory is formulated, it tries to introduce a force fields for this U1 invariance, which shouldn't have been gauge fixed, because it's really a rigid symmetry. And the result of not only fixing this U1 gauge symmetry is having a ghost zero. Okay, so these four harmonic zero modes are essentially coming from the ghost anti-ghost sphere on the D instant term and the ghost anti-ghost sphere on the anti-D instant. And so the remedy for fixing this problem, these integrals, is that we simply undo the gauge fixing by using a gauge invariant form of the path. So we use a gauge invariant form of the string field theory and use the gauge invariant form of the path. Okay, so that gets rid of the ghost zero modes. Okay. But that of course means that you have to use some additional integrals, okay, that we have not done earlier, okay, because they are only done a gauge fixing, okay, and you have taken back on all this. So this I am not discuss any further because this is a well-tested procedure and this has been verified. This is known to work in many examples, okay, where the answer is known from again some dual description. So this includes, for example, the C equal to 1 bosonic string theory, C less than 1 bosonic string theory, type 2B string theory and D equal to 10, okay, type 3 or type 2B string theory and Calabi-Yau Clifford. In each of these cases, the result is known from some dual analysis, okay, dual description, and this procedure always gives the right answer. So we just quote the final result of carrying over this procedure. This is the confidence. Okay, the divergent angular Spartan function that we saw is essentially replaced by an integral of this form. And here the idea is that this is only the angular spot, but x1, x2 integrals have to be done only at the very end after we take the product of this, the integral, with the d square functions, okay, because they also depend on x1 and x2. So the main point of this string field theory analysis is to fix this normalization. Then it's 1 over 4 pi square is a factor that comes out of string field theory analysis. And this normalization factor, in fact, was determined earlier by this paper by Balthazar Rodriguez and in that I mentioned. And they got it by comparing with the matrix models. So they had an expression like this with some arbitrary normalized, because that normalization was a divergent factor because of these divergences that I showed you. Okay. So they just fix the normalization factor by saying that what we need to, they asked what do we need to for the results to agree with the matrix model result. And they found that normalization factor has to be 1 over 4 pi square. And this is exactly what comes out of the string field theory analysis. Now, string field theory analysis also tells us that we have to deal with the poles. You see that there are poles at x1 minus x2 equal to plus minus 2 pi. That's where the open string modes from stretching between instanton and anti-instanton becomes cyclic. And so string field theory analysis tells us that the poles at x1 equal to x2 plus minus 2 pi needs to be treated using the principal fiber expression. Okay, and this is needed for preserving unitary. And this again is something that DRY checked, that it's only with this prescription that the amplitudes computed this way agrees with the matrix results. Okay. So for the instant or anti-instanton contribution, okay, the result for string field theory seems to agree with the matrix. But as we will see that there are some puzzles. So one of the puzzles, and the puzzle comes with the about the certainty about unitarity. So it's denoted by Mn as the n instanton or anti-instanton contribution to the S matrix for scattering from some state A to state B. So let's consider the simple case where A is just a closed string amplitude with closed string state coming from the right with energy omega 1, and B is a final closed string state chi r again to the right of energy omega. Okay, so a closed string state of energy omega 1 comes in and reflects back with a closed string state of energy omega 2. So this amplitude we can calculate based on the formula that I gave earlier. Okay, this formula over here. times the least one functions, whose expressions I had already written down earlier. And what one finds is this. Okay, this is the result for him. In a unitary theory, we know that the S matrix has to be unitary, so S diagonal S should be 1. So this translates to the instant and induced amplitudes to the relation of this form. And here I am using the fact that the perturbative amplitude is unitary by itself. So the perturbative amplitudes has no conflict with unitarity. Okay, so they don't contribute either positively or negatively to unitarity. So now we are asking whether the instant and induced amplitudes are unitary. And so this is what we have to have in order for the instant and induced amplitude to be unitary, right? Because M2 plus M2 star is not 0, you can see. Right? So this basically says that the M2 by itself is not a unitary S matrix. If there is an I here, it will be unitary, but there's no I here. So M2 plus M2 star is not 0, but that's okay. It can, in principle, be equal to this. But now we have a puzzle because this is supposed to vanish. M1 have argued that single D instant or amplitudes or single anti-D instant or amplitude is 0 by infrared. So if this is 0, we have a problem with it. Right? It violates unitary. So you have a contradiction because I just argued in the previous slide here that with the principal value prescription, we should get a unitary constant. Okay, so now I want to ask what is happening, right? Where is the argument breaking down? So now we have to review where the argument came from, and then we'll see what exactly is happening and how we can restore unitarity, and then generalize this result to calculate the semi-inclusive cross section. So here I have rewritten integral amplitude in a somewhat more complicated way. So let me explain this formula. So the first two lines of this formula are exactly that expression that I wrote down for the annulus particle. I have just added and subtracted various, right? For example, this term over here, H and epsilon are arbitrary positive numbers at this stage, and H is the state function. So this term, for example, it has cancelled this, right? It is added and subtracted this term. Here I have done the integral from epsilon to infinity, and this step function essentially provides the rest of the integral from 0 to epsilon. Right? So this becomes an integral from 0 to infinity of -2, and then this is the other contribution that came from the open string state between the instant and analysis. And these are the these quantum. This is the expression that we had. Now let's start analyzing this. So we'll first analyze the first slide, because this is the easy part. So for small epsilon, what one can show is that if we take this slide, this is of course finite integral. Okay, and the result is given here. Okay, for small epsilon. This one is divergent. It has divergence from the t goes to infinity. There's no divergence from the t goes to 0 end because you have cut off the divergence and epsilon. Cut off the integral ends. On the other hand, the t equal to infinity, you have already argued that that's the open string divergence, and then you can get finite answer out of those. And using that formalism, so we find that this integral is actually given by this expression over here. Okay, this dx1, dx2, of course, has to be done after you take the product of this, right? Because this also depends on x1 and x2. This also depends on x1 and x2. So now I'm going to describe how to deal with the second line. This line. So here are the steps we follow to analyze the second. So first, we change variables S, which is 1 over 2. Why? Because S is the closed string channel showing the pattern. Then we represent S dependent integral as a result of momentum integration in the closed string channel. And then we'll do the AC. So at the end of all this, the claim is that the M2 that I wrote down actually can be written in this form. Okay, this is the expression for M2. Now, if you want to see this, the easiest way to see the equality of this and the second line that we wrote in the last slide is that we write first of all the 1 over k square in the Swinger parameter representation. Okay, we basically go backwards. You first write 1 over k square in the Swinger parameter representation, where the Swinger parameter is s. Then carry out the k integral. Carry out the k integral. You will get an integral in terms of s. And then you make this change of variable from s to t. And you can convince yourself that you get back the earlier result. Okay, so this is just rewriting of the original result. And at this stage, you can examine this and you can convince yourself that there is no divergence from the small momentum region. And that is a reflection of the fact that the original expression that we started with had no infra divergence in the closed string channel. Okay, t goes to 0 limit of. But what we'll do now is that we'll put a lower cutoff theta on P and then manipulate the term by writing this as a sum of terms, each of which diverges and each diverges. Because you can see that if we, unless we have this particular combination, right? If we try to split it up, then individually they can diverge from the lower end. Yeah, and we allow it to we allow splitting of this term, but we just keep a lower cutoff theta. And at the end, of course, you will say theta equal to 0. So the result of this is that the expression that you had after you expand out the exponential, we can actually express this as the sum of Feynman maps of string field. And here is the Feynman diagram. See, okay, the 1 and 2 are the external lines. These are the closed string propagators, okay, propagating in the loop. And there are 3 kinds of vortices. This is a de-instanton induced vortex. This is the anti-de-instanton induced vortex. And then there is a composite vortex, which is here. And I'll give the Feynman rules in the next slide, although they will not be very illuminating. Okay. But the claim is that after you follow those Feynman rules, okay, we can resum these diagrams and recover the exponential that I wrote down in the previous slide. Okay, so it's an exact, entirely equivalent way of rewriting what we had earlier in the language of string field. So I have the very expression from the various vortices. Okay, the purpose of giving this is just to show that everything is explicitly known. Okay, what these vortices are. This is the de-instanton induced vortex, this is the anti-de-instanton induced vortex, and this is a composite. And this includes this integration over y, right? Y that we mentioned, this is the same as the variable x1 minus x2 that we had. Okay. And the idea is that the reason that we have to use this principal value prescription for doing the y integral, okay, is that it's only under that condition that this particular vortex corresponds to a real term in the closed string field reaction. Okay, if you use any other prescription, okay, you will have a complex closed string field reaction, and that of course is not expected to give a unitary result. Okay, to get unitarity, you need real action. Here are the rules, Feynman rules for the properties. Here how to do the internal movement. Now, what is the advantage of writing this as a sum of Feynman? Right? You have a nice simple expression, right? Exponential of one single term, and you have just tried to mess it up by writing it as a sum of many infinite terms. The advantage of writing this as a sum of Feynman diagrams is that now we can just use cutting rules, right? In order to test if the amplitude is unitary, right? We just use Karpowski rules because that Feynman diagrams always satisfy cutting. So, in particular, this quantity of interest, right, minus M2 plus M2 star, is just given by the sum of cut. Okay, and the only kind of cut diagrams that we have of this 5 diagrams that I showed are these 2. And here let me again emphasize that the ability to write these as a sum of cut diagrams, okay, relies on the fact that the string field reaction is real, right? And that requires a principal value prescription for doing the x1 minus x2 integral. And now we can interpret these cut diagrams as M1, right? This is the single de-instanton induced average. So this is like M1 dagger M1 induced by de-instanton, and the other one is like M1 dagger M1 induced by the anti-de-instanton. So this is of course the statement of unitarity. So now again we run into the same puzzle because M1 is supposed to vanish by IR, right? So what's happening? Right? We are argued earlier that M1 is 0 by R due to infrared. But now that we have explicit expression, we can answer that question. And so what turns out to be the case is that if we keep the number of Cart propagators fixed, and then sum over all possible virtual closed string states, means these and these, whether if we keep these numbers fixed and sum over all possible virtual closed string states, then indeed the result will vanish. And it vanishes as we take the cutoff eta to 0. And this is the physics here is the same as in quantum electrodynamics. Right? The virtual loops gives you an exponential of a negative infinity, and that makes the QED amplitude vanish, right? With any finite number of final set charge coordinates. But we can fix eta, and then first sum over all possible Cart propagators, and then take the eta goes to 0 limit. Then it turns out that we get a finite result, and this agrees with the unitarity prediction. So this is the way unitarity is restored. Okay, again, the idea here is the same as in quantum electrodynamics. Okay. There you fix your infrared cutoff. Okay. You sum over virtual and the real emission loops. Okay. And then at the end you take the infrared cutoff to 0 and you get a finite result. Right? And the same procedure here is a finite result for the this M2 plus M2 star, right? The inclusive cross, the sum of all final states. Now, once we understand how unitarity is realized, we can in fact now do more. Right? We can compute what we call the semi-inclusive process. So let me explain what the question that we asked. What is the question you are trying to answer? So semi-inclusive cross section means that we are trying to calculate the cross section for producing a fixed set of closed strings in specific energy range plus anything. That if in the final state, we don't say that we sum over all final states. That was the M1 dagger M1. But we say that in the final state, we fix certain set of closed string states with fixed energies or fixed energy range, and then we allow the rest of the energy to be carried by anything. Okay, that's what is called the semi-inclusive cross section. And this can be done easily in terms of this diagram, right? In terms of this Cart diagram, because what we have to do now is that in some of these Cart propagators, we have to fix the energies. So you fix the momenta, that means energy and momentum of a finite set of Cart propagators, and then sum over the rest. And this specification of what final state closed strings look like, they can be done either in the NSR basis or in the AR basis, chi-L basis. And it turns out to be a little convenient to use the chi-L basis. So that's what you do. So we take the incoming state to be a single chi as before, and allow in the final state a certain number of chi-L, certain number of chi-L, and then anything. And this is the result. What one finds is that the semi-inclusive cross section, which means this sum over the prime, means that on the left hand side, we sum over all final states that contain R right sector closed string states of energies in this range, and L left sector closed string states of energies in this range. And then, of course, we allow any number of other closed string states. It's result. Okay, you can calculate exactly in the way I said. Okay, in the Cart propagators, you fix certain number of the energies of certain final states, and then you sum over the rest. Okay, and that turns out to be infrared finite. Okay, just as in quantum electrodynamics. And this is the result of this. Okay, this is the result that we get from this sum. And here I should note for when L is larger than or equal to 1, that means there is at least one closed string state on the left. The incidental contribution is a leading, because automatically when you throw in a closed string from the right, everything reflects. So it's the incidental contribution that leads to transmission to the left. And what we had seen earlier is that transmission of a single formula seems to indicate that we do not have a closed string description in the final state. What this analysis shows is that it is true that we don't have a closed string description in terms of a finite number of closed string states. Okay. But a third one on the left and the third one on the right can be given a closed string description in terms of infinite number of instances, right? Because you do have a finite design for such applications. Okay, so since my time is up, let me just skip the next detail that in a matrix model language, you can also do this calculation. Okay? And the calculation there, in fact, can be much simplified by saying that the final state, okay, when you say the sum, we sum over everything else, that everything else can be chosen in any basis that we like. And the calculation seems to be simple in the harmonic basis. And once you do that, okay, that calculation doesn't suffer from any infinite divergence at all. Okay? And at the end, we basically get to the same result as, so you get a simple integral of this form. And this, after you do this integral, one can show that it agrees with the string theory. Okay, and as I said, this result has no infinite divergence at any stage. Okay, so the matrix model result doesn't see any infinite divergence. The string theory side sees the infinite divergence, but at the end it gives the same result as the matrix. Okay, so I think I'll just stop here. And again, let me congratulate you for your very successful career and wish you all the best for the next 60 years.
Thank you for the beautiful talk. Okay, questions? Comments?
No, I'm just saying you didn't take complete revenge, just perfect timing.
You know, this function I couldn't have not know, right?
Yeah, that is one question. So here you deduct the Feynman rules by going backwards. Starting the answer in the right is kind of discover the Feynman rules. Is there more starting with the string field theory in earnest and then derive with everything?
Yeah, there is, but the point is string field theory itself is constructed by going back. Because the way you construct the string field theory action is in order to reproduce them, right? So I made it very explicit here. But if you just follow the general rule for constructing string field theory action and derive the Feynman rules, you get exactly this.
I see. Okay, great. Thank you.